science. It's one of the only institute of its kind that brings together people for sustained collaborations over a semester. We bring the top people in areas of theory that we choose based on proposals that we get from the community. So you are the community. So feel free to propose to us programs that you'd like to see. But besides doing core theoretical computer science, we use the theory lens, the algorithmic lens, to understand other areas of endeavor, intellectual endeavor, like economics, physics, neuroscience and psychology lately, and even closer to home, just understanding machine learning from a theoretical point of view has become a big focus for us in the last couple of years. We had a whole year-long program on large language models last year, and on modern paradigms and generalization as well. Besides these long-term programs, which are our main bread and butter, we occasionally do workshops of this kind, which we call exploratory workshops, which are basically looking to see if a theoretical lens can be fruitfully applied to a different area. In this case, this area is probably not different. It's kind of theory, kind of not, but I like this title here, Graph Learning Meets TCS. That's what we want to understand. How does it meet TCS exactly? So we're looking forward to this workshop and thank the organizers, Chris and the others. And I'll hand off to Chris in 1 minute. There's one little housekeeping rule here, and I see that I don't even need to mention it. We don't allow any food or drink in this auditorium. So please leave whatever you're drinking or eating outside when you come in. Thanks. Enjoy the workshop.
Thanks a lot. So is my microphone working? All right, so first of all, a warm welcome from my side. So I'm Christopher Morris, one of the organizers. And first of all, a warm thank you to Sampath for the kind words and also for hosting us here. We very much appreciate the opportunity from the Science Foundation to be here and bring together the TCS community and the graph learning community. So let me just say a few words what this workshop is all about. So you probably know this already, otherwise you wouldn't be here, but just to be sure. All right, so maybe let me start with the workshop organizers. Some of which, or most of which are here. Maybe those can raise their hands or quickly stand up. So what is the aim of the workshop? So as you know, graph learning is an active area in machine learning. And in the last 5 years or so, there were many interesting interactions between graph learning, TCS, and also applied mathematics. Right? So tools from TCS were applied to graph learning to get a better understanding for graph learning. But it turns out that the current landscape is somehow fragmented, and hence the aim of the workshop is to somehow provide or work on a more unified perspective on graph learning within TCS. And we also want to identify major challenges arising from this interaction. So what are the current limitations of current tools from applied mathematics and TCS applied to graph learning, and how can we extend those? And importantly, we will also want to discover areas within TCS that could benefit from a richer interaction within graph learning, so that we can also discover new areas or different areas in TCS that could also be applied to graph learning and help us to derive a better understanding of graph learning. And then also vice versa. We will also want to look if ideas from graph learning can be used in different areas of TCS. For example, it has already been done in combinatorial optimization. So Andrea will later talk about this. All right, so here you see the overview for the week. So today, on Monday, we will have a bootcamp day. So we will give different boot camps on different topics to get everybody up to speed. Then on Tuesday, it will be on logic, theoretical computer science, and graph theory. The chair will be Floris Gertz and Michael Benedict. Then on Wednesday, we will talk about generalization theory. Chair will be Stefanie Gelka. And then on Thursday, we will talk about combinatorial optimization. Chair will be Andrea Lodi. And then on Friday, it's all about geometry and applied mathematics. And the chair will be Matthias Niepert over there. All right, so what's the plan for today? So we're currently in the welcome, and then we will start off with a first bootcamp on graph learning. So this will be a general introduction to graph learning to get everybody up to speed. Then we will have a 30-minute coffee break, and then another bootcamp on invariances in graph learning, so invariances to group actions. This will be led by Nadav Deem, Rizi Konda, and Hannah Lawrence. Then we will have lunch. So lunch is on your own, but of course I hope that you guys group up. And then after lunch, we will have another bootcamp on graph fonts for graph learning. This will be led by Luana. And then last not but least, we will have a bootcamp on graph foundation models by Michael Galkin. And then in the evening from 5 to 6, we will have the reception. And if you want to have a more detailed schedule for the whole week, you can scan this QR code. I will also show this at the end. Or you could also type in this URL on the bottom of the screen. And these are just some organizational remarks. I think Sampath already said this. So no food and beverages are allowed in the auditorium. So let's stick to the rules and be respectful. And we need to leave the auditorium at 5 p.m. sharp because the staff wants to go home. Right? And this is everything from my side. So let's have a very fun and exciting workshop. And we're going to start with the first bootcamp by Ameya Velingker and Haggai Maron from the Technion.
Maybe we can, okay, we can try that. Yeah, let me just, oh, this has power?
It already has power, yeah.
Okay, let me just, okay.
And that clicker should already be connected.
Oh, I see, okay. All right, thanks for the introduction. Can everyone hear me okay? All right, awesome. Yeah, it's my pleasure to be here, and I'd like to first of all thank all the organizers who've put in a lot of work to make this workshop happen, and thanks also to the Simons Institute. I think it's a great mission here of the workshop to bring together two distinct communities, the graph learning communities as well as TCS. And I've actually been fortunate to have been a part of both of these communities over the years, going back to my grad school times. And in fact, I think the first time I visited the Simons Institute was exactly 10 years ago as a grad student. So it's great to be back here for this talk. And okay, yeah, so this is just kind of the set of speakers here that are part of this first boot camp on graph learning. So our aim is to give you some overview of the area, the types of questions, kind of maybe some basic framework for what will hopefully come over this week. So I'll start with the first half an hour or so, and then I'll pass it to Haggai later this morning. And yeah, feel free to stop me and ask any questions if something doesn't make sense. I'd like to make this as interactive as possible. And it's a pleasure to give the first talk here because hopefully all of you are sufficiently caffeinated and full of fuel. So I think this might be the first time I've actually given a talk under certain circumstances. OK, so just to give you some overview of the list of topics, we'll start off with fundamentals of graph learning, so talking about things related to what sort of tasks we look at, kind of early methods, moving on to more modern topics over the last few years, and then finally touching on graph transformers. And basically, this will be my portion of this bootcamp, and then I will pass it on to Haggai, who will discuss the expressiveness and topics related to that. OK, so let's start with an introduction. So I think we have a lot of theorists in the room, a lot of graph learning people. So really, I think everyone knows what a graph is, but just to make sure we're on the same page, basically it is a set of nodes, optionally with some kind of features, combined with a set of edges that connect pairs of nodes. So you can represent the connectivity or the topology as an adjacency matrix. So these are basically designed to capture relations between entities. And the area of graph learning is really, has a number of applications in various fields where you can actually describe a lot of the problems we want to solve naturally as a graph. So for instance, molecular graph problems where you have this natural graph structure coming from molecules and bonds connecting different atoms. You have similarly knowledge graphs where you have different entities as nodes in the graph, and maybe there are certain connections between different entities and you want to learn things about them. Social network graphs, things like road network graphs also, where you might want to predict traffic in a network. And generally speaking, we can combine our tasks into a few different types. There's kind of node level tasks where we want to predict some property of the actual nodes in the graph. So these are things like node classification. You can also have node regression, which classification is more discrete. Regression, you want to predict some quantity, or maybe cluster nodes. You also have things like edge level tasks where you might want to predict the existence of links between different pairs of nodes, or maybe do things like classifying edges. And you might also have tasks at the graph level, where you want to predict some overall property of the entire graph. So I think most graph learning tasks can be categorized into one of these three, such as the ones I mentioned on the previous slide. OK, and to kind of encapsulate maybe just kind of the overview of what the challenges are for machine learning on graphs. So we've seen a lot of successes in deep learning over the last decade or so. One thing to note is that a lot of the advances we've had have been on sequence or grid data. So things like if you go back, starting with convolutional neural networks, they were designed for working on grids of pixels. Okay, for vision tasks or image data sets. Similarly, we've seen transformers in more recent times, and they operate typically on sequences of tokens, or basically things coming in order. Now, graphs, on the other hand, have more general topological structures, right? So if you look at a pixel grid, for instance, or an image, generally, each node kind of has the same neighborhood. It's this very regular grid structure. But in a graph, you might have a more general structure where local neighborhoods of different nodes can vary. There might be some dense portions of the graph. There might be some sparser portions. So one question is, how do you identify, or how do you reason about nodes within a graph? So just to kind of crystallize this intuition that I alluded to on the previous slide. If we take a look at convolutional networks, for those of you who are familiar, there's this filter that, we call it the convolutional filter, which basically gets moved around this image, and we take some kind of linear combination of different pixel values. Right? And the idea is that you can capture some kind of local neighborhood structure on this grid graph. So again, the graph here is where you connect each pixel with its neighboring pixels. Okay, and this is basically how convolutional nets work. Similarly, for transformer architecture, you have sequences of tokens. And you're typically doing something like a next token prediction. And if you want to cast this into some kind of graph language, you can think of it as a graph, as a line graph, where things are, words or tokens are coming in sequence, and you're kind of connecting everything on this line. OK, so just keep those examples in mind. I'll get back to them in a bit. Any questions so far? OK, I'm seeing some thumbs up. So some people have gotten their coffee. OK, so before I kind of dive into kind of the more modern topics, I'm going to start a little bit with these early methods. So these are things that were prevalent maybe a decade or so ago. So the early methods of learning on graph structured data involved what were known as node embeddings or graph embeddings or kernels. And the idea was to map nodes into some kind of low dimensional embedding space. And the idea is that nodes that are similar should have similar embeddings. OK, so these are manifested in methods such as deep walk and node to vec, again, about 10 years ago. And they incorporate a lot of techniques based on random walks, things like matrix factorization. I think all of these are of interest to the theorists in the room. And similarly, you can do things at the graph level as well, involving graph kernels. OK, so just to give you an illustration, the pipeline would look something as follows, where you map every node into some low-dimensional embedding. And then on top of that, you use these embeddings to do things like graph clustering or link prediction, node classification, et cetera, pretty much any task that you want. OK, so how were these node embeddings typically learned? Or what are the properties you want? Well, again, I said that similar nodes should have similar embeddings. So you can use some kind of similarity score. Typical kind of simple one is to look at inner products, where two nodes that are similar should have a pretty high inner product, or their vectors should be kind of aligned. And how do you train these? Well, you can use a supervised approach, for instance, where you have certain tasks that you want to optimize for with labels of ground truth data. And then you can pretty much learn node embeddings according to these tasks. You can also adopt an unsupervised approach, where you learn these embeddings according to some structural aspects. OK. I should note that one technique that is used for these node embedding constructions is random walks, where you can determine the similarity of two nodes according to whether they occur together in random walks, or whether they're likely to occur. And again, I think random walks are something that many here probably look at. But they capture local information, because at each step you're kind of moving locally in the graph. But if you take a long enough random walk, it also tells you something about multi-hop information, more global information. And there's this intuition that kind of if pairs of nodes don't occur or are not very likely to occur on random walks together, maybe these are not very similar. So this is a measure that looks solely at topological information in the graph. And the general strategy that some of these approaches I mentioned previously use is to basically sample random walks according to some strategy. And then you can collect random walk statistics. And then using these, you can basically define, you can construct some embeddings, and you define a loss, which you can train using gradient descent. And this is indeed kind of essentially the idea behind these early works, such as deep walk and node to vec. The main difference lies in how the random walks are sampled. In deep walk, you're using fixed length, unbiased random walks starting from every node. And in Node2Vec, you use more biased random walks, and you can actually kind of control this parameter that allows you to trade off between kind of doing more local exploration versus doing more global exploration. So something like BFS versus DFS intuitively. Okay, so this idea seems very simple, but lo and behold, deep walk was actually able to show its promise on a number of tasks. So there's this one famous graph called the karate graph, which I think a lot of graph machine learning folks used to look at. I don't know how much people look at this, but it's a nice kind of simple example where you're supposed to predict these node labels. So they're clustered into these communities. And you're supposed to only look at the topological information. So there's no additional features. And using something like deep walk, it was able to basically classify these nodes correctly. OK, so that's kind of how the general node embedding approaches of a decade ago worked. So what are the problems with these approaches? Like, what are the limitations? So generally, one is that it's hard to get embeddings for nodes that you haven't seen during training time. So if you have sort of new graphs that you want to test on or dynamic graphs, it's unclear how you can take this embedding data from training and kind of apply it. The other thing is that while you do get some structural properties across long distances, generally the random walks are still somewhat limited, and it's unclear that you're truly leveraging long distance information to the fullest extent. And then finally, most of these approaches were based on kind of looking at topological structure of the graph. At least the early approaches, they weren't really concerned at incorporating node or edge level features. So that's also another common challenge. And the solution that has emerged essentially is what we call graph neural networks for deep representation learning. And that's basically what I'll describe in the next few minutes. So before I kind of arrive at a definition of graph neural nets or GNNs, I want to kind of go back to this example that I mentioned to folks to keep in mind, which is this intuition from convolutional nets. So what were the salient aspects of this kind of convolution filtering approach for images? The idea was that the filters capture some local neighborhood information on the graph. And you have some kind of weight sharing, right? So this filter, let's say, for instance, in this example, we have a 3x3 filter. Here, the filter size does not depend on the actual size of the graph, right? So you can have much larger images, the filters is the same. So you have some kind of weight sharing. GNNs essentially generalize this intuition to general graphs. But one of the challenges, as we'll see, is that these neighborhood structures look different, right? In a grid graph or in a pixel graph, every node pretty much has the same structure around it, right? Like you're connected to pixels above, to the left, to the right, and below. The only exception is sort of on the boundary of the image, but you can pretty much extend it and just kind of zero out things that go outside. OK, so that brings me to the next part, which is graph neural nets. OK, so what are graph neural networks? The main idea is that you perform some kind of message passing approach where each node communicates with its set of neighbors or topological neighbors in the graph. And the idea is to combine node features of these neighbors from the previous step along with potential edge level features or global graph level features. OK, so in this particular example, you have this node x2 connected to x1, x3, et cetera. So a message passing step would entail these neighbors kind of passing messages to x2, and then you do some kind of combination of the information. OK, so let's make this a little bit more formal. So you start with initial set of node features, which I call HU0 for node U. You have some edge features. And then you iteratively perform these L message passing steps. So think of it as L layers in your deep network. And the first step is kind of this message M, which goes from V to U. It combines the features, the node features of U and V from the previous step, that is the tth step, along with the feature of the edge. Okay, so that's the message here. Once you have these messages, you want to combine them. So for message U, I got this multi-set of messages from all the neighbors V. So that I'll have some learnable, or I'll have some function F, an aggregation function. And one thing to note here is that you might have multi-sets of different sizes because some nodes have more neighbors than others. So you want this to be some kind of function that generalizes to multiple arguments or variable number of arguments, and is also permutation invariant. So you shouldn't depend on kind of the ordering that you choose in the graph of the nodes. So typically you can use things like sum or max or average, things like deep set. Also, it's a more sophisticated approach. And then the final step is to combine this aggregated value or vector you got with the node's own feature via some learnable function f update. Okay, and then this basically gives you the node feature of U at the next time step. Yeah, go ahead.
You don't update the edge features?
Yeah, I mean, in this setup, I think the edge features are kind of just given to you. Yeah, we're updating the node features. But you could potentially do that too, yeah. Okay, so then the idea is you do L layers of this message passing approach. You get some final set of embeddings for each U. And then depending on the type of task you're doing, you're going to have some kind of appropriate readout layer. And for node level, for instance, for an edge level task, you might combine the features of the two nodes on the edge. Okay, so just to give you an example, it might be useful to kind of work through this. So let's say I start with this node, or start with this graph, excuse me. And let's say that these colors kind of indicate initial features. So let's say all the nodes have the same features except the top node, the one that's colored in orange. So the first thing I'm going to do is like some kind of aggregation step, where for each node, I'm going to look at the set of neighbors, or the multi-set of the colors of the neighbors. And then I'm going to map it to some new vector or some new color. Right? So in this case, the nodes that have two blue neighbors map to orange. This one, which has two blue and one orange, maps to blue, et cetera. So this is kind of the message passing step. And then I combine these two graphs to get the graph on the top bottom left corner. So for instance, for this bottom node, I have a blue here and an orange here. So blue and orange combine to green. Okay, so I can do some number of steps like this. This is basically like a pictorial representation of what I was doing on this slide. Does that make sense? Any questions? Yeah. Okay, so yeah, you can kind of keep doing this. I'm going to skip over this, but essentially it's the idea that I mentioned just now. Okay, and then there's a few different kind of instantiations of this paradigm. So I'll go over just a couple of basic ones that were popular. So one is graph convolutional networks. I think the easiest way to kind of look at it is this equation here, where you have some column stacked set of node representations. So you have n columns for each of the n nodes. And at each step, you kind of multiply by this normalized adjacency matrix. And then this W is your actual weight matrix of learnable parameters. Okay, and then you apply this nonlinearity. So this is what is called the GCN. And you can also describe it using this notation that I defined a few slides ago. But I think it's kind of easiest to think about it this way. But for instance, you can think of the messages as this previous node feature normalized by the square root of these degrees. So that's coming from this d to the minus half left and right multiplication. And then you do some kind of addition of all the neighbors. So you can check if you spend enough time that these are equivalent. Another popular method is GraphSage, where one of the kind of key ideas here is that you can actually do some sampling of neighbors. So they look at kind of more than just one hop of neighbors. They look at 2 hops and do some sampling of neighbors because you might have too many neighbors to aggregate over. And again, you can kind of describe it in this language that I defined earlier. One final example I'll go through is graph attention networks. So here you are actually, one of the interesting things is that in this aggregation step, you're actually assigning importances to different neighbors. So you actually use an attention mechanisms to compute a score with different nodes. And the idea is that ones with higher score, you want to actually aggregate with a higher weight. Okay, so the way it looks is kind of you do some kind of computation, and don't worry about it too much, but it's some sort of softmax calculation. You compute these attention scores for all the neighbors V of U, and then this message aggregation step actually, it doesn't do a basic sum, but it actually weights by these attention scores. Okay, so before I move on, any questions on that part? Yes, no? Need more coffee, anybody? Okay. So the final kind of section of this I'll talk about before I hand over to Haggai for the last few minutes as graph transformers. So this is kind of this alternate paradigm that has emerged over the last few years. So again, I remind you of the vanilla sequence-based transformer as outlined in Vaswani et al. Here you have a sequence of tokens. This is typically like an NLP task. And you want to do some next token prediction based on some previous context window. And in graph language, again, you can think of this as a line graph. So graph transformers are essentially extensions of transformers to graph structure data, where instead of doing next token prediction in a sequence, you're actually learning node embeddings. And
so it is true that the input is given to you as a line, but then when you do attention, you consider the complete graph.
Yeah,
yes.
yeah, that's true. Yeah, so and I think in the graph setting, it's all often also full connections where you connect everything. But I think there is sort of a more, I guess what I want to say about the line graph is there is a logical ordering of kind of the tokens, whereas in a graph, it's unclear. There isn't really a single ordering, right?
You consider the order because you have positional encoding, right? So.
Yes, no, yeah.
Correct, yeah. So with graph transformers, I mean, again, I think as you alluded to, you often have connections between all pairs of nodes. So this does result in some kind of loss of inductive bias compared to this message passing approach, where you are actually kind of taking the topology of the original graph more strongly into account. So one question is, how do you identify nodes within the graph in this kind of transformer architecture? Also, how do you scale things? Because again, if you're connecting all pairs, you get this kind of n-squared bottleneck. So again, I'll kind of try to move fast here, but the kind of most basic framework for graph transformer came out in this paper of Dwivedi and Bresson in 2021. And it's again, basically the same QKV kind of attention approach with some minor tweaks. But here again, the input is kind of your node representation from the previous step, and the output is a node representation that you're outputting after this layer. And again, I think we mentioned positional encodings for regular transformers. So in the graph world, we also have this, but just to describe kind of the sequence world, if you remember, we have these kind of sinusoidal encodings. This was what was used in the original transformer paper. And then there are these kind of newer approaches like rope and alibi, et cetera. In the graph world, also we need some kind of way of identifying nodes in the graph. Again, it's not a line graph, but it's potentially more complicated because with the line graph, you could do actually just kind of a basic sinusoidal. Here, it's a little bit less clear. But what comes to our rescue is actually graph Laplacians. And I'm not really going to go into too much detail here, but if you kind of look at the eigenvectors of this graph Laplacian, which is basically the adjacency matrix with some modifications, you can get these eigenfunctions that give you a logical positional encoding. So one way to look at it is in your transformer, sequence-based transformer world, the sinusoidals that are used for positional encodings, they actually arise as Laplacians of sort of a line graph. So if you kind of apply this intuition to the graph world, you can look at more general Laplacians of graphs. And then generally what happens is you take these eigenvectors, and maybe you take the first few eigenvectors of interest. This is just kind of an illustration. I will, yeah.
But in the positional encoding, usually you don't have an assumption of how long is this line. Here in the case of graphs, what is the assumption of how we would continue a graph in order to have a complete analysis?
Yeah, I mean, so I guess the sinusoidal is like a pretty, it's a pretty simple function, but there's still like an n that comes up in the argument, right?
But it's up to the user, independent on the input that you then choose. Here you have to start with a graph, and the user cannot change something easily so that it can.
Yeah. I think that's just kind of the nature of the beast. I think in the line graph, I mean, it's characterized by a single value, right? And so in the graph world, maybe it's a little bit too much to hope for something like that. So as I mentioned, in the graph world, there are Laplacian encodings, but you can also do things like learning encodings on top of these Laplacian-based features, with some kind of trainable approach. And this is actually what was used in this one early graph transformer approach called spectral attention networks. And again, there were some experiments done on some popular graph data sets that showed that actually the graph positional encodings also make quite a bit of difference for these transformer approaches where you're not doing simple message passing. Just to give you another example, there was another kind of early approach called Graphomer, another graph transformer approach where they also used some sort of positional encoding. What they actually use is something called centrality encoding, which combines this kind of learnable function of in degrees and out degrees of a node. And then they also have some kind of attention bias that's based on shortest path distance. So it's same old KQV, with these two centrality and attention bias encodings. And they were able to leverage this to get kind of state-of-the-art results at that time for some pretty large molecular graph data sets. Okay. Then the kind of final thing I'll mention in terms of challenges with graph transformers is scaling. So again, if we are connecting all pairs of nodes, in addition to the kind of inductive bias issue, you also have this quadratic dependence. Again, there have been a lot of approaches kind of for transformers over the years in the sequence world to mitigate this issue. And there's this nice survey paper from a few years ago that had a Venn diagram of all these different approaches. I think it's a little bit outdated now. I think over the last 2-3 years, there have been some more advances, but gives you some flavor of things. So the idea is, again, that you want to kind of maintain good global connectivity, but be able to do things that are basically have an efficient computation. Okay, and for the graph world, there have been similarly a number of approaches, things like XFormer, NodeFormer. I think pretty much if you take any sort of concept and add former to the end, probably somebody has done it. I think if there's anything to take away from the slide, that's probably it. But they encapsulate a bunch of different approaches to kind of reduce this dense computation and make things more linear in the size of the graph. So just to give you one example, this is something we worked on a couple of years ago, which is XFormer. Here the idea was that you use edges from, instead of computing this complete graph and doing attention over all n-squared pairs, you look at edges from the original graph combined with some edges from an expander graph. So I know a lot of theorists in the room probably have used expanders for other topics in theoretical computer science. But they have these nice random walk mixing properties that give you some kind of global connectivity. So, but they're a spectral approximation of the complete graph that has a linear number of edges. So this is kind of the general idea of XFormer, and then we have these kind of global sinks that are connected to everything. And then this was able to kind of improve some results on various benchmarks. So just to kind of summarize, we introduced this graph neural network approach based on message passing, and then we talked about graph transformers as well. So again, with the message passing approach, the advantage is that you get this inductive bias of the graph topology via the edges over which message passing takes place. The computation is efficient. Again, it's only linear in the number of edges and nodes. But they struggle a bit with long-range dependencies. In fact, if you do L layers of message passing naively, you can only really communicate with nodes that are at most L hops away, right? So if you have a graph with very large diameter, there are certain pairs that can't even communicate. To some extent, you can mitigate this with features, and I know Haggai will be talking a little bit about this later. And graph transformers, on the other hand, you can allow the computation graph to be different from the input graph. So this enables kind of more longer range connections more easily. But identifying these nodes within the graph and sort of this loss of the inductive bias are issues that arise. Also the n-squared computation. But some of the approaches that I mentioned with positional encodings and sparse attention can mitigate these. And then I'll just mention, finally, there's this nice work called Graph GPS from a couple years ago that actually combined both approaches. So it kind of alternates between message passing layers as well as graph transformer layers. And you can kind of get best of both worlds. So finally, I'll conclude with a shameless plug to a tutorial that I gave last year at ICML, which has some more resources on these topics and others. You can scan the QR code, I guess. And that's sorry. Yeah, that's all I have for you now. And thanks for listening. And I will pass it over to Haggai at this point.
Okay, so I will talk about expressive power of graph neural networks. First of all, thanks a lot for the other organizers, especially for Christopher for organizing this. I think it's a great gathering here. So expressive power is an interesting topic in deep learning in general, and in graph neural networks, I think it's even more interesting. I will try to convince you. Just have to say that this is heavily based on a learning on graphs tutorial. Learning on graphs is a relatively new venue for graph neural networks and learning on graphs. And yeah, we gave a tutorial in the first one. And this was written mostly by two students that I worked with quite a lot, Fabrizio Frasca and Beatrice Bevilacqua. I should say that Fabrizio is currently my postdoc, and he is looking for an academic position next year. So if you want an amazing researcher in your university, ping him. OK, so yeah, I'll go over it quickly. Graphs, we know what they are. We have a node set, we have an edge set, and we have a bunch of node features. Node features are usually organized in a matrix, which is of the size number of nodes by D. We might have also a global graph feature or edge features as well. Here we will assume that we only have node features, but nothing really changes if you assume that you have also edge features, for example. And as we all know, we can represent a lot of interesting phenomena with graphs, molecules, social networks, communication networks, and so on. And the way we usually represent graphs in graph learning is by using those two matrices. One is the adjacency matrix. It's n by n, where n is the number of nodes. It represents the connectivity structure. And the other one is the feature matrix, which gives a d-dimensional feature for each one of the nodes. A central idea is the one of graph isomorphism, which we probably all know. And isomorphism is a bijection between two graphs, between the node sets of two graphs, that preserves the adjacency structure and the features. So if we have node features, it should preserve the node features. If it has edge features, it should preserve the edge features, and so on. So here is an example for two isomorphic graphs. And what we can see is that they have different matrix representation, right? The two matrices are not the same, but they represent exactly the same graph. The way to think about it is that those isomorphic graphs encode the same structure, but they are organized in a different way. The nodes are permuted in a way. But as far as we care for graph learning, we don't really care about the order of the nodes. We just care about what is the graph that is represented there. And we want to be invariant to these kind of permutations. So to see it more formally, the way to move between one representation to the other representation is essentially by multiplying by a permutation matrix from both sides. So doing that gives you the adjacency matrix of the other graph. So what are graph neural networks? Ameya did a great job of telling us about those. The way we think about them in this part of the talk is they are just parametric functions over graphs. So we have the set of graphs that we're interested in. We have f theta. F theta is going to be the parametric model. Theta are going to be the learnable parameters inside. And we're going to mainly talk about models that will map the graph to RL, which is just vectorial representation of the graph, right? You can think about other things, get node features, edge features, and so on. We will talk about mainly about global graph features. Okay. So as Ameya said, most popular flavor of GNNs is probably message passing neural networks. The way they work is by combining or concatenating several message passing layers, here denoted as mu, and then a readout layer. The readout layer is kind of a pooling layer that takes all the information from all the nodes and gives you a global representation for the graph. So one pretty popular way to do that is the following. The message passing step, which is pretty similar to what Ameya showed, is going to be to send messages between each node and its neighboring nodes to aggregate over them. The aggregation can take several forms, but it should be invariant to the order of the neighbors. And then you will have an update function that will update the messages, the aggregation of the messages, essentially, with the previous node representation. If you want a global graph feature, then what you're going to do is usually to aggregate over all the nodes in the graph. So you see the sum here is over all the nodes, and here it's only on the connectivity. So here we sum over all the nodes in the graph and then apply something. And the functions that we use for update, message, and apply to the pooling is, in most cases, just simple MLPs. So what's good about message passing? They are quite efficient. The computation is linear in the number of nodes and edges. This is nice because we're going to see that there are methods that are going to be quadratic or polynomial in general. The computation takes into account the graph structure in a very strong way. So particularly, we perform the message passing. So we kind of encode the graph structure nicely here. And some people claim that this is a good inductive bias. And we have this locality kind of idea, right? So locality is kind of embedded nicely into this procedure. Those layers are what we call equivariant. We will define this in a minute, but the way to think about equivariance is that it respects the natural symmetries of graphs, or symmetries of the representation of graphs. And if we talk about the global graph feature, it will be invariant to those symmetries. When I talk about those symmetries, I'm talking about the permutations of the node features and the adjacency matrices. So here's the formal definition of equivariance and invariance. A function on graphs is going to be equivariant if applying a permutation to both the adjacency matrix and the node feature matrix gives us node embeddings that are permuted by the same permutation matrix P. So essentially, the function commutes with the permutation operation. It is invariant if the output doesn't change in case we apply those permutations. And for all graph learning methods, we really want them to be invariant or equivariant. This is a very good inductive bias because we don't really care, except for very, very extreme cases, we don't really care about the order of the nodes. A nice thing about MPNNs is that they really respect those kind of things. So MPNNs are equivariant or invariant to node permutations. OK, so the fact that graph neural networks are invariant to node permutations gives us one good thing, which is if we take two graphs that are isomorphic, we will get exactly the same output from any GNN. That means any number of layers, any parameters, whatever you do in there, you will get exactly the same output. And this is good for us, right? We don't want the learning algorithm to try to understand which graphs are isomorphic to each other. It's kind of currently encoded in it. What we would also like to have is to have distinct representations for non-isomorphic graphs, right? So if I have two graphs that are not the same graph, you would like to be able to separate them or to be able to predict different things on those graphs. So here is an example. This is the graph world, in which we have multiple isomorphic graphs in each one of those circles. And we know that we would like graph neural networks to map each one of those to the same thing. This is invariance. But to map other equivalence classes under this group action, essentially, or symmetry, to different points in the feature space. Okay? If, for example, we have two non-isomorphic graphs and we do want them to predict the same thing, then we can potentially do that with a downstream classifier that will be applied to the GNN representations that we got. So it doesn't restrict us to have separation. So this brings us to the first problem, and a very major problem, of MPNNs. And this was a breakthrough in our community done by Stephanie's group and Christopher and other people. And they showed that there are pairs of non-isomorphic graphs that cannot be distinguished by message passing neural networks. So let's see an example. Here we have a representation of two molecules, decalin and bicyclopentyl. Those are clearly not isomorphic. But any GNN that will be applied to those two graphs will give you exactly the same output. So you can see here that we have different isomorphism classes, essentially. But the MPNN, because of the way that it is built, the design of the MPNN, we will get exactly the same output. It's pretty easy to show. I will not show it here. And this is, of course, a big limitation. For example, let's say that the function that I want to learn is to count the number of 6 cycles in the graph, right? So I will need to output two different things. Here we have 2 6 cycles, and here we don't have any, right? So I want to output 2 and 0, but I cannot do it with MPNNs. So those papers in 2019 kind of gave rise to a whole, I would say, direction that with hundreds of papers, I think, on the expressive power of graph neural networks, trying to get graph neural networks to design graph neural networks that are more expressive. For example, they might be able to tell those two graphs apart. Here is another example. So here we have two graphs. Those graphs are not isomorphic, but both of them are 4 regular graphs. And if you think about it, message passing cannot really tell the difference between them, right? The idea is that in each step, the node looks on the neighbors, and it sees 4 neighbors, which have uniform features, and this doesn't change along the computation. OK. Separation is one aspect of expressivity, and we see that we have a problem with separation. But there are also other ways in which we can think about expressivity. So one of them is being able to count substructures. And for example, and this is the example that I gave before, let's say that we have 2 graphs, and I want to be able to count the number of cycles in them, which might be interesting for some downstream task. So if I use MPNNs, I cannot really do it. And we already saw an example, right? Those two molecules have different cycle counts, but MPNNs will output exactly the same thing on them. There are multiple ways in the literature that people use in order to quantify the expressive power. And specifically, in those two papers from 2019, a nice connection was done to something that is called the Weisfeller-Lehmann graph isomorphism test, or 1WL, or color refinement. So what is the Weisfeller-Lehmann test? We all know that figuring out if two graphs are isomorphic is not an easy problem, but people came up with heuristics to do it, and this is maybe the most simple heuristic. The idea is that you start from two graphs, and then you perform message passing or color refinement operations. So in each step, you take the current color of the node and the set of colors, the multi-set of colors of the neighbors, and you hash them together into some node representation. You do that again and again until you get a stable coloring. So for example, this is what you get after one iteration. After two iterations, you will get something like that. And if the coloring is not changed, you can stop. Then you can compute the histogram of the colors that you have on each one of the graphs. And if the histograms are different, then those two graphs are not isomorphic. If they are the same, they might be, and might not be. OK, so essentially, the result that was proved is that message passing neural networks and this color refinement algorithm, they kind of have the same expressive power when it comes to distinguishing graphs. And this shouldn't be very surprising, right? Because essentially what message passing neural networks do is to aggregate information from the neighbors, which is kind of what we do here in this step, and then update the node feature with the previous one. So essentially what you can show is that if you choose the right weights for a graph neural, for an MPNN, you can implement a version of the color refinement or the WL algorithm. So the Weisfeller-Lehmann test is not like a single test. It's actually a hierarchy of graph isomorphism tests. So you have a KWL test for any k natural number. And what it means is that we have a hierarchy of separation powers. So we talked about 1WL, and then for any k that is bigger than some k prime, you will get a graph isomorphism test that is more expressive. So it can separate all the graphs that we were able to separate with the lower version, but even more. OK, and this idea, I think, gave rise to maybe the first set of methods that people suggested as more expressive GNNs. So again, those methods came from Christopher and other people. And what they tried to do is essentially to mimic the KWL computation step. KWL works on k-tuples of nodes instead of one node. So you get something much heavier because you want to work on like a tensor of k-tensor of nodes and to update it in each step. The graph neural networks that were suggested to mimic that, they have more expressive power. They are tied to the expressive power of KWL, but they cost much more computationally. So we get another point on this trade-off between efficiency and expressivity, I would say. So let's try to see what we have in the landscape now. The y-axis here gives us the expressivity, and the x-axis gives us the computational complexity. So we have MPNNs. Gene, for example, is one representative type of MPNN. Yeah.
Does the K stand for the number of hops?
Sorry?
Does the K stand for the distance between the nodes?
No, K stands for the number of nodes that you take into account in the KWL step. So you take k-tuples of nodes and you update them.
So it's not
No. Let's maybe see here. So here we see k equals 2, and what we are updating is tuples, like metrics with tuples of nodes. If k equals 3, then we have an n by n by n matrix that we need to update, and so on. And then there are a bunch of methods that are tied to the KWL expressive power. And we can see that they give us more expressive power, but also much higher computational complexity, which could be problematic. So just to give you a hint about what's going on, I don't think anyone implemented KGNNs for more than 3, right? Someone did? Yeah? But probably it can work on graphs up to size of 5. I don't know, something like that. Christopher will correct me later. So those things are very nice theoretical constructions, but no one really uses them in practice. So how to measure the expressive power of GNNs? So we typically use them using some pairs of disambiguated graphs. There are all sorts of different graphs that people suggested. There are circular skip-link graphs that we saw before, which are regular graphs. There are strongly regular graphs. There are pairs of KWL distinguished graphs. And in each one of those papers about graph expressive power, you will most likely see an example of how the new method can separate two very peculiar graphs, and the other methods cannot. Other ways to think about it, as I said, is to being able to count the substructures in a graph and to approximate general functions. So we can definitely think about approximation power in graph neural networks as the function approximation problem, right? You have a space of IJCC matrices and node features, and you want to approximate invariant functions on top of this space. So this is a clearly defined mathematical question, and this is one way that you can go about it. And as I said, the quest here for the last 6 years was to come up with more powerful GNNs. And we always take into account also the not only the expressive power, because we saw that we can go up in the expressive power, but also the computational complexity. So one maybe first method that you will come up with if you want to solve this problem is something that we call node identification. And the idea is that one of the problems with message passing is that you don't really know who sends the message. You only have the node feature. And in many cases, node features are uniform across the graphs, or they don't give enough information in order to disambiguate the nodes. And the idea here is to solve this anonymity problem. So let's try to understand how this anonymity looks like. Let's say that we have this graph and we perform message passing over it. So in the first iteration, what the node, let's say that we are in this node, what it sees is the following. We have a set of...
Can I ask a more philosophical question?
Of course.
So how much more expressive power you want, right? You know that KGNNs will not be able to recognize all pairs of, they will not be able to recognize graphs up to isomorphism.
Right.
What is it that we really want here?
That's a good question. I think it really depends on the downstream application. In certain cases, message passing is good enough. I think many benchmarks that we currently use in our community, message passing neural networks do very well. In other cases, I think more combinatorial cases in which you don't really have informative node features. So if you want to solve, for example, a combinatorial optimization problem, let's say that you want to find the max click in a graph, right? So expressive power is going to be an issue, right? So it really depends on what you're trying to do. There are some applications that will require more expressive power, and there are some applications in which you don't really need it. Okay, so what we see in this first message passing step is that our node sees 3 nodes with the same features. In the second step, the main node sees that every node sees, every neighboring node has this structure around it. But at this step, we cannot really tell the difference between this graph and this graph, right? Those 2 graphs gives rise exactly to the same type of representations. How anonymity solves this? So we are going to give node features, different node features to each one of those nodes. They are depicted here as colors. And then after 2 steps, we can reconstruct the graph directly because we know exactly who sent each message and so on. So this is a clear way to solve this problem. And actually, when I tell people that I work on this problem, they always say, OK, so you just need to add some unique features, and that's it, right? That solves the problem. And yeah, people actually tried to do that. So how do you do this in the most simple way? So you can think about adding to the X matrix, which is the node feature matrix, a new matrix R, in which you get some unique identifiers, right? So you can think about just one hot identifiers, for example, for the nodes. You can think about different things. One particular thing that I want to show you is using random node features. And there are 3 questions that come up here. So how to choose those identifiers, what is the expressive power, and does it really work? So let's see. So this was a pretty influential paper from 2021. They suggested random GNNs. And random GNNs, what they do is just in each forward iteration, they sample R, a matrix of random node features. Let's say that we sample from some continuous distribution, then with probability 1, you will get different node features for each one of the nodes, and you can disambiguate them, right? And then you just train the network using those node features. It's easy to see that you can always distinguish nodes, but this is kind of not fair, right? Because we have them different node features. And one good thing about it is that you don't really, if we think about the one hot encoding idea, then we need to add node features or identifiers that are as large as the number of nodes. Here we can just decide on the dimension of the random node features independently of the size of the graph, which is kind of nice. From expressivity point of view, so it is possible to show a result of expressivity in probabilistic sense. So there are weights that with high probability will be able to approximate any invariant functions on graphs. So we have that. But the problem is in practice. In practice, we see that it's extremely annoying to train those kind of networks. So what we can see here is a gap in the training curve between standard GNN and GNNs that use random node features. And in practice, people don't really use them. They are quite well known to not work well. So it's a first thing you need to try, but it doesn't really work. I think that getting those things to work well is a nice challenge for our community, if it is possible, right?
I was curious about that. As we use the random feature, will not it break the invariance or the equivalence property of the graph? Because as we random each time,
right,
the result will be broken, so it may be different for...
The function itself, the message passing neural network, will be invariant, right?
Yeah,
but each time you sample different features, and that will give you different representations for the same graph.
Yeah.
Yeah, so this is indeed a problem.
Yeah, because under the paradigm of the RMPN, the random generator is a part of the algorithm, right? So it will break the equivalence or the invariance property.
Yeah, you can think about this
conventional
this way.
chain. Okay.
So you kind of break the inductive bias that you want to
Yeah,
have.
I see. Okay.
By the way, you can always apply an MLP to the representation of the graph, right? To the adjacency matrix. And then you can separate anything you want, but this doesn't work well as well.
Yeah, it's
Right?
really
Yeah.
Why does it have slower convergence? Like, what are the reasons that you get like worse training?
I'm not sure if people truly understand why this is the case. I think it has problems generalizing because it has to learn to be kind of independent of the node features. So the learning task is more is harder in a sense. But I'm not sure if people like have clear understanding of why this happens.
I mean, the function space is just larger, right? The sample complexity is also higher, obviously.
So where's the figure from? So in the paper, there's some dependence of these results on the details of the randomness?
Yeah. They have some. I think they tried with different type of randomness and with different dimensionalities of random features.
No, for the theory.
For the theory?
Yeah.
I think they just assume uniform random features, but I need to take a closer look at this. Okay. So we have a new method now in our landscape, which is RMPNN. It's up here, which is kind of optimal as far as this illustration goes, right? Because it has lower complexity and high expressive power. But we do have those three triangles, which is problems with optimization and with invariance and with selection of the random features and so on. So this method might look like a good solution, but it doesn't really work. Okay, so we go next to another set of methods that people suggested, which I call feature augmentations. You can call them structural encodings as well, as we will see in a second. So just to recap what we had until now, we had higher order GNNs that kind of mimic the KWL tests. They are permutation invariant. They are expressive, probably more expressive, but they are polynomial and doesn't work in practice. On the other hand, we have MPNNs with node IDs, and those are not working, essentially. So we want to find something maybe in between. And one way to think about it is equivariant node identification. So maybe we can come up with new node features that we can attach to each node that will allow us to tell different nodes apart. And one very simple way to do it is to use substructure counts. So the idea is that there are certain substructures like cycles that we cannot really count with MPNNs. So we can just count them before and add them as a feature to the graph. And this, of course, will give us something that is more expressive than message passing neural networks. How does that work? So you choose a substructure bank, H. Here we have a 6-cycle and a 5-cycle. And then you look for all the occurrences of those substructures in the graph. And then you add them as extra node features. So this is pretty straightforward. And then what you actually do is just perform standard message passing with those extra substructure counts. So these are the original node features, and those are the additional counts for the bank H. So of course, you're not going to be less expressive than MPNNs. And if H contains things that you cannot really detect with or count with MPNNs, you will be more expressive. Another idea here is to use homomorphisms instead of isomorphic copies. So essentially, when you look for substructures, you look for the exact substructure, but you can also think about a slightly more general approach in which you are counting the number of homomorphisms between substructures and the graphs. And this was suggested by people here in the audience. And this is another interesting approach. People also use it in graph transformers. So we have this addition here to the landscape, right? We have H GSNs, H is the graph, and depending on the H is the bank of the substructures, and depending on H, we will get different expressivities. Although usually you don't get something that is aligned with the KWL, you get something in between. The main criticism about those kind of substructure counting methods is that you need to know what you want to count, right? So people come up with, okay, cycles is interesting for me, I will count cycles. But this is pretty much against the philosophy of deep learning, right? When we work on images, for example, we don't really add, I don't know, a SIFT and other kind of image features to the input. We just want a neural network to be able to recognize what's interesting, what is something that we can use in order to make the right, to compute the right output. And this is kind of cheating in a sense, because you have some prior knowledge about what type of things you are looking for. If you know, that's great, and those methods work well. But if you don't know, that's a problem. OK, this brings us to, how are we doing with time? 10 minutes? OK. OK, brings us to another set of methods called subgraph GNNs, which were also suggested by multiple people here in the audience. OK, so let's see what's going on. Do another recap. We have higher order GNNs with their problems. We have node ID, MPNNs with node IDs with their problems. We have those substructure count MPNNs, and they require domain knowledge. And we want something that doesn't have this restriction, so something more general. And yeah.
On the previous slide, you said that substructure variables of linear complexity, but if you want to count 5 cycles or 6 cycles, you can't do that.
Right. If it's 5, like constant, then it's OK. But
OK, so n to the 5 is the linear.
Right.
OK.
Yeah, so there is a pre-processing step that you need to take into account, but the actual computation is going to be linear, right? OK, so in general, what we want is like expressive and efficient and equivariant models, right? And subgraph GNNs tried to strike the balance between those things. The idea is kind of nice and intuitive, I think. So there are graphs that are WL indistinguishable, but if you look on subgraphs, and very simple subgraphs that you can get from those graphs, you can actually pretty easily kind of tell those graphs apart. So let's see an example. So we have those two graphs, and if you try to run message passing or color refinement over them, you will get exactly the same color histogram, although clearly they are not isomorphic. This is what you get, right? You get those colors and the same outputs from any MPNN that you will apply. But let's say that we look on the set of edge-deleted graphs. So that means to go over all the edges in the graph, and then you delete a single edge at each for any edge. So instead of looking at the graph, you are looking at a set of subgraphs that you get in a very specific way. It's pretty easy to see that if you run WL or message passing on those graphs, you will get separation. Okay? So this is a good intuition to what we would like to do. Instead of looking at the graph as a graph, we will look at it as a set of subgraphs and then apply graph learning algorithms to each one of those subgraphs. We call this set of subgraphs bags of subgraphs. And it's pretty clear that using this approach will give us more expressive power. So let's see how it really works. For an input graph, you will get the set of all the graphs that you can get by removing a single edge. You will do it for each one of those graphs. Then you can apply WL to each one of those independently. And then you will get a histogram of histograms, essentially. And this has more expressive power. OK. So essentially, we need to understand two things here. One of them is how to select the subgraphs. And second is how to encode the subgraphs. So there are multiple different selection policies.
The learning process is applied over this bag of subgraphs?
Yeah, okay. And you can also share information between them, and this gives rise to a slightly more expressive methods. Okay. Okay, so what kind of things we can do? We can, like, very simple stuff, right? Node deletion. You can perform edge deletion. You can take the ego networks, so the local networks around each node. You can take marked ego networks. This is also something that we tried. So you mark the root node of each subgraph. And you can think about many other things that can be done. So you get this bag of subgraphs. And this can be seen as slightly problematic step, because you do need maybe some knowledge about your graphs in order to select the subgraph selection policy. But arguably, it's less, depend on this less than on the substructure counts that we discussed before. So this is more general. So next thing that we need to discuss is how to come up with an encoder. I will go over it quickly because I don't really have time. The way we did it, as we shall see later, many people did it in a different way. The way we did it is by trying to understand the symmetries of the object. So what we have here is a set of subgraphs. We have two different things that we want to be invariant to. We want to be invariant to the order of those subgraphs. We don't really care about this order. And we want to be invariant to the graph symmetries, right, the permutations. So if you think about it from like geometric deep learning point of view, you have a symmetry group that looks like this. It's SM times SN. SN is a symmetry group for the graph. SM is the symmetry group for the set. And you want to be invariant to that. And in the literature, there are some ways to come up with networks that are like recipes to come up with networks that are invariant to those kind of transformations. This gives rise to something we call DSS-GNN. Essentially, you encode each subgraph independently, and you have some information sharing part between the subgraphs. And people showed that this gives more expressive power. OK. So I think it was like 3 years ago, and we worked on it, my group, and then we discovered that many other groups work on this in the same time, including Christopher and Floris and Boang, Zhang and Mohan Zhang and Pan Li, and other groups, prominent groups that work on graph learning. So all those people together started to work on this at the same time. I'm not sure why. So you get this wave of subgraph GNNs. People came up with many, many different flavors. And there was a need to analyze them and to kind of understand what's going on. I will not get into too much details, but what you can show is that if you use what we called node-based subgraph GNNs, in which you select the subgraphs according to each one of the nodes, like in correspondence to each one of the nodes, then you can show that these kind of things are bounded by 3WL. So this gives us the following landscape, right? We have like subgraph GNNs that sit here between 3WL and 1WL, and they are slightly more costly or less efficient because you need to perform message passing over all the subgraphs. OK, we are near the end. I want to mention several works that are great, but I didn't have time to talk about. Those works come up with general frameworks for understanding the expressivity of graph neural networks. So if you're interested in this topic, take a look on them, including Best Paper Award by Floris, and another honorable mention from last year. So those are general machine learning conferences. People seem to like this direction a lot. There are also several surveys also from people in the audience like Stephanie. And there is also a 4-hour version of this talk from the original log conference that we had. It's online. You can watch it if you're interested. OK, do I have 5 minutes? OK. So the last thing I want to say is something about maybe more general structures than graphs. So people recently look on high-order structures. You can think about hypergraphs, for example, connecting multiple nodes, not only pairs of nodes. And the umbrella term that people use is topological deep learning in many cases. Okay, so you kind of have a more general way of representing relational data. And the main structure that people use in this field is called combinatorial complex. It's pretty simple. You have a node set. Okay, it's a 3-tuple. You have a node set S. And then you have X, which is just a bunch of subsets. And you also have a rank function, which is less interesting. So the idea that those subsets can encode high-order relations, right? Because you can encode 3 nodes. You can think about higher-order structures and so on. So this is a really interesting and promising field. And what people currently do is something that really reminds us of message passing. Okay, so the way you operate, like the main question of this field is how to build a neural network that can operate over those structures. And what people do is like just a generalization of message passing. So those subsets, they give rise to new adjacency structures, right? So you can think about nodes that are shared within subsets, or subsets that are connected because they have a non-trivial intersection, and so on. This gives rise to a lot of adjacency structures. And essentially what those high-order message passing neural networks do is to just perform message passing over those graphs. And of course, like a natural question would be, what is the expressive power of those creatures? So in a recent paper, we showed that they have expressive power limitations as well. So this is not surprising, because essentially what you do is you apply message passing to a graph representation of the underlying object. What's more interesting is that although it is called topological deep learning, you cannot really detect simple topological properties using this approach. So for example, you cannot understand orientability. You cannot detect other types of properties, and so on. So just to give you an idea of why, so think about the operation that takes the boundary of those two manifolds here. So the boundary here would be 2 6 cycles, and here it would be a larger cycle for all the nodes. And we know that message passing neural networks cannot really differentiate those two things. So this gives the idea of how the problems with message passing neural networks pass to topological deep learning and high order message passing. Yep, so just to conclude, designing expressive and efficient and effective neural networks is a very interesting topic. It was the main thing that many of us in the audience worked on in the last few years. There is slightly less papers, I would say, in the last 1-2 years. But still, there are some interesting things to understand, I think. One of them is that usually, or in many cases, the analysis takes, assumes that we have unbounded network ability to use unbounded network sizes. So the question is, what happens if we have a budget, for example? If you have like several layers, or you have a budget of the number of parameters that you can use, and so on. I think those things are less clear at this moment. Also, an interesting general question is, can we characterize the expressivity and complexity trade-off here in a nice way? Because currently, as we saw, we have this landscape, and we just put things on the landscape. But trying to understand what you can do with certain complexity, for example, what graphs you can disambiguate or not, I think it's an interesting problem, and at least I don't know a good answer to that. Yep, so I think that's it. Thanks a lot for listening, and I'm happy to talk about it. If you want, just catch me in the break. Any questions? Yeah.
How to situate graph transformers in this expressivity?
Yeah, that's a good question. So it really depends on the node features that you add. So usually people use two different things in order to augment. Because if you think about the graph transformer, you don't really use the adjacency structure in it, because you use the full graph, as was said before. Then you need to encode the graph structure in the node features. So one way to do it is to use structural encoding. So people try to encode number of subgraphs and so on, or some information about random walks, for example. And people also use graph positional encodings, as Ameya mentioned. And this gives rise to another like bank of information that can be used in order to disambiguate graphs. Problem with many of those positional encodings is that they introduce some kind of ambiguity. So for example, if you take the eigenvectors of the Laplacian, then you have sign ambiguities or general rotational ambiguities, and this gives rise to essentially graph representations that can separate the same graph from itself. So you lose invariance in a way. Yeah, but definitely, trying to understand the expressive power of transformers is a part of this. Yeah.
Follow up. So, I mean, can't you decouple the node embedding you can do for an NPNN or for a graph transformer, right?
Mm-hmm.
And then, given when you talked about node embedding, which may be a little different than those, but it's the same idea, right? And the graph transformer itself is, I would assume maybe slightly less expressive than an NPNN?
It's less, because you can think about it as a set network, essentially, right? What's a transformer? It's something that is generally invariant to permutations of the inputs, if you don't give it like positional encoding. So I don't think you will get extra expressive power from using this approach that you mentioned.
Right, like not clean expressive power. Maybe like better ability to avoid over smoothing, which in a way does increase in expressive power.
Yeah.
So maybe let's move the discussion to the coffee break. So we continue at 11.